Hey, folks. Welcome back. I've been trying to answer some questions. Um, I think I've answered a couple, and just to sort of vocalize a few things. There was one really good question I just answered, and that is, all right, if you're running something with your Python API in your notebook here, and it's, as I've mentioned, it's running something on a server somewhere else, is it okay for you to close your notebook? And the answer normally is no. And the reason is you have to remember we're opening a channel of communication. So when we first start um, our um, our notebook, there's the let me go to it here, I suppose. The um, sorry, I'll do this. Well, there's the initialize command, and what you're doing is you're opening a channel of communication over the internet between your computer and a Google server somewhere, or if you're using Colab, between the server that's hosting your Colab notebook and then another server that's hosting the data. And you have to keep that line of communication open. If it breaks, then whatever you're working on will probably get demolished by the servers to keep things from going crazy. So in other words, if you lose your internet connection, or if you close your notebook while you're in the middle of processing something, you will lose that process. However, the very reason that that happens is why they have what are called tasks that you can create and send to the servers. I'm not going to get into the details there, but if you Google Google Earth Engine task, T-A-S-K, basically, especially if you're exporting data to Google Drive or something else, that's something that's going to take a while, seconds, minutes, perhaps hours. And so what you do is you create a task, which is a set of instructions, and then you send that task to a server, and then it does that processing. And then if you leave your computer, if you drop your computer out a window, it doesn't matter, that task will complete. And then as long as you can access the Google Earth Engine and you know your task ID number, you can get that information. I've done a lot of work in terms of API pinging data from NASA and NOAA, and a lot of the processes that are involved in that are similar. They take a very long time. So what you do is you basically send requests to the server and you can walk away. But it's a great question, but to answer it simply, for us here using these notebooks, if you're running a process and you shut your notebook down, the process will be killed. So just keep that in mind. And it's also why the things that we're showing you today are fairly simple, smaller calculations, because we don't want to lose our work, but that is something to keep in mind. Okay, and I also noted, I think someone else was having some issue with the Timor-Leste geometry. There probably is a coordinate reference system issue there. I don't know why that's not working for you in the Colab notebook, unless it's some typo or error in the code that I'm not aware of. I'll take a look at that, but it should work. I just did it live with you guys, but I'll look into that. But perhaps we can resolve that. But I want to keep moving on here, and I'm glad people are kind of trying this out, even if you're running into errors. It tells me that you're at least giving it a shot and engaging with this stuff. Welcome back to the section, final section of the day. And I'm going to just get right into it. And I'm going to try to keep this to 45 minutes or so. We might go a little bit past it. It's up to you guys, but this is the final section of the day. So we're going to get through some practical examples and then I'll just leave a couple key takeaways. But if I lose you or if you have to jump, please just hang on to that link. We're going to send this video to everybody for one thing. And we're going to include, of course, the link and perhaps I can make this deck available too with all these links, but they're all the tutorial. So it's all sort of coming from the same place. Okay. All right, so let's chart some time series. I'm going to reopen my Jupyter Notebook session. I keep inadvertently closing that for some reason. And while I'm doing that, if you can navigate in your tutorial to module 4, submodule 1, which is called time series charts. That's the page I have up here, and you can open up this notebook as before. Open it in Colab. While I download this locally, here we go. Okay, so and you know what? I'm gonna open this one in Google Colab too. No rhyme or reason, just trying to switch it up a bit. Okay, so One note about charting here. And some of you have encountered this when you've been trying to work with creating the tile layers to create the slider panel. It's actually pretty complicated to pass data back and forth like we're doing and make plots and displays. Unlike what people think, when most of the software packages and the libraries that we're using, when you're creating plots, you're not just displaying an image. You're actually drawing the data points directly into you're drawing them, so to speak. And so if you're plotting something that you're displaying on your screen, it's necessary for you to actually pull the data that you're plotting from wherever it lives on a server somewhere, and that can be complicated work. You have security issues, obviously passing data around from servers. You have a lot of data that you're trying to manage. There are maybe a number of reasons why Google Earth Engine has not made this chart module available that are beyond my ability to understand software engineering wise, but it is a kind of a complicated process. So just keep that in mind. And that is why sometimes it's hard to do the functionality that we're doing. But there is a module there called the UI for creating charts. And if you go to the Google Earth editor, you can create time series, you can create histograms. It's fairly straightforward and there's a lot of documentation there. Feel free to explore that if you want, but for sure you can plot things using the Python API, and that's exactly what we're gonna do. There's just an extra step involved in that you have to extract the data. Okay, so what we're gonna do is we're gonna take a look at some VIIRS data. And we are going to, first of all, grab it for a fairly precise location, not necessarily a point, I guess I should be more technically precise, but an area around a point. And then we're going to look at the sum of lights for all of South Korea. So I chose somewhat arbitrarily Seoul Olympic Stadium as my point to analyze. Since we are in Google Colab, we do need to install these libraries. One thing to note, we are installing, we need to install GMAP. That is a typo. If you're following the lab, you need to type in GMAP. I forgot to do that. I will update that, but you can do that right now. We're installing multiple packages. We're installing the GMAP library. We're all familiar with that. We're also installing the matplotlib library, and then we're installing a library called Seaborn, which is useful for plotting in Python. Now, there's a method called histplots that I like in Seaborn, but it's only available after a certain version. And I tested it. For some reason, that version is not on Google Colabs. So I need to pin, this is what's calling pinning a version. I need to say, not only I want you to install Seaborn, but I want you to install this particular version of Seaborn. This is, I have to say something you need to do very commonly with open source data. We love open source data for many reasons, but it is something you have to keep in mind that there are a lot of versions of libraries floating around, and sometimes it's necessary for you to tell people or computers exactly what version you want. So I should have been installing this while I was talking because it'll take a few seconds, but that's installing these libraries and that we're going to use for plotting. And just so you know, Seaborn is in the, if you were to just install it, you would get Seaborn and it would work fine. It just doesn't have a histogram method that I like because the people that authored that package, I guess, added it later. Okay, so now I'm going to import these libraries, including these plotting libraries, because I'm coming back to this after closing out my Colab session. I need to re-authenticate. And so I'm going to do that here momentarily. Okay, and now we have, okay, so what are we doing? Well, we've done this before. We're getting our point lat and long for the Seoul Olympic Stadium, and we're going to create a buffer of 500 meters radius around that point. That's called our POI, or point of interest. We're saving that as a variable. Okay, now we're collecting VIIRS stray light corrected monthly composites, and we're going to collect those for a series of time from January 2014 up until through May of this year. Okay, so there's going to be obviously a few dozen images in this time series. Okay, now we're going to create a very simple function here. I know it doesn't look simple, but I'll walk you through it. We did the reduce region before when we were getting the data from Timor-Leste, but before we had clipped the data to the Timor-Leste shape. This time we haven't done that yet. So when we pass our image, it's going to be the entire file that covers the whole planet. In this case, the composites are global. So when we say reduce region, we're going to tell it to reduce it by taking the average pixel value, But then we also are going to pass it our geometry. So we're going to say we want to get the mean, but we only want to get the mean of the pixels that fit within this particular point of interest. The scale parameter is quite important, and I'm going to talk about that later. But this basically scales the grid that it's using to define what falls in this geometry, and this is in meters. So this is a 30-meter scale. This actually becomes quite important later. And we're gonna, as always before, we're gonna get the average radiance band for these data. And then what we're doing here is we're basically saving that as a variable called mean. All right, this is the average for these pixels. It's a number, okay? And what we're doing is we're actually adding this information to our image itself by adding this as metadata. You're gonna create a label called date, and we're going to put this data into a format that's easy to read so that later we can actually plot this and we know what the data is. We don't have to deal with the Unix timestamps and all that mess. And then we're going to create a label called mean, and we're going to set our mean value. So what's happening with this function is it takes an image and then it reduces the pixels, the data of the pixels by getting the average, the mean for everything in this area that we're giving it. And it's going to do it for this band. And then it's going to add that data as metadata to the image itself, and then it's going to return that image. So if I were to do this on a single image, it would give me just the mean value. But what I want to do is do this for our entire collection because we're doing a time series, recall. So what I'm doing is taking that function named POI mean, that's what we just wrote up here, and I'm going to map it to every image in our VIIRS image collection. And then I'm going to get POI reduced images, okay? Now, this is where things get a little bit fuzzy if you're not used to working with data structures. When you're working with data, again, I think it's helpful and perhaps important to know that it comes in a bunch of different structures. You may know lists, we know arrays, we know images, which are really just arrays. This function here produces a data structure that is a list of lists. So what we get are values. And what we're doing is we're extracting from these images just the date and just the mean. That's all we're interested in. And so we get a list here for each image that has a value for date and a value for mean. And then we're getting the list of all of those. So each image in our collection. Again, it's okay if you don't follow me, but essentially we're getting a nested list. And we want to turn that nested list into something we understand better as humans. It's just easier to read a table. So we're going to use the pandas library. And I've saved that pandas library here. This is a very popular, very powerful library in Python for working with data frames, table data. So I've saved that as PD, and it has a method called data frame. And what I'm going to do is I'm going to take this nested list structure. I have to do this callback so that I can actually get pulled. What I'm doing is pulling this information from the server. I'm turning it into a table. And I'm going to name these columns date and mean. And so you see here printed out below, we have a table. This makes sense to me. I have a column that is the dates, and I have a column that are the mean values for a point of interest. This is a time series. Now, these dates are kind of wonky. This is a string, and what I would rather do is turn these into an actual mathematical object that I can use for calculations, and it's easier to read. Thankfully, Pandas has a method that does that very simply called toDateTime. And by passing it, and if you guys are familiar with R, the syntax for a lot of this is very similar. And by the way, if you are using R, once you get your data into this format, obviously you can take it from here in R if you want. But basically, I'm selecting my column vector of date, and I'm going to transform it to a date time object so that you can actually do mathematical calculations like the difference between two dates and that sort of thing. And I also like it because it just is a better format. And I'm going to set this to the index. And the reason I'm doing that is so that when I plot this, the x-axis will actually be our index. So now we can actually make a plot. And so this should look familiar. We're going to create a map, and we're going to call it Korea map. We're going to center it on our point of interest. We're going to set the zoom level to 13. We're going to add a satellite base map. And now all I'm doing right now is just showing you this on a map, because obviously we want to visualize what we're looking at. All right, so here you have Seoul, South Korea, and here is our point of interest, a 500-meter radius circle around a point that's about the center of Seoul Olympic Stadium here. So this is the area that we're actually collecting our data from. So when we collect our data, Matplotlib and Seaborn are libraries for plotting that are pretty popular. Plotting is fun and interesting, can get a little complicated. We're keeping this simple. But basically, we're creating a canvas here that we're going to be drawing on, if you want to think of it that way. The figure I'm going to set is a specific size. You can adjust that however you want. There's a default too. But basically, I'm taking the data that I just created, that data frame, and I'm going to plot it as a line plot. And this makes the time series. And I'm going to call the y-axis mean radians, and I'm going to call the x-axis date. And then what we're looking at here then is a time series of the mean radiance for the pixels within our area of interest, which is Seoul Olympic Stadium, from January 2014 until May of 2020. And keep in mind, because these are monthly image composites, that's the time period that we're looking at. So if you look at this time series, you can do some quick analysis. Clearly, we have some noise. Perhaps, as Dr. Elvidge mentioned, we're seeing some not quite annual cyclic data here, but it does seem to be somewhat cyclical. Perhaps that's not surprising for a stadium that has seasons of events, I would imagine. What you, I'm sure, are noticing is a spike here. There's an anomaly in our time series that's quite apparent. We also see what looks like some kind of a decline, perhaps, and then a drop here in 2020. So these are things that we can now quickly, I mean, if you run this code and you're familiar with it, all this just takes seconds, and all of a sudden we're looking at a time series. Now, the underlying data is a data frame, and there's a method called IDX max. What that does is it says, get my max value. And there's only one column, but if there were multiple columns, I could say, mean or whatever column I want. But what this does is it gets the max value and it returns the index, which is the date. So I can see that this max value here, I can visualize it, but I can also see that it is for September 2018. So I actually did a little bit of Googling, and I was like, okay, well, what's the big deal about September 2018? Why is there a spike there? And I found out that 2018 happens to be the 30th anniversary of the Seoul Olympics. And we're looking at the Seoul Olympic Stadium. So perhaps there are some events commemorating that happened in September. I don't know, that's just a guess. But what excites me about data science is that this is an anomaly or an event that we looked at just purely from the data without knowing anything else. By looking at nighttime lights data, I'm able to infer some kind of event and might lead me to other inquiries. And obviously, if you work with time series analysis, you know that anomaly detection is a very common and very powerful use case for time series. And so here in just a matter of moments, we've been able to identify a time series for a region. You can also smooth it out. With our pandas, we have a rolling method, and we can provide a window. In this case, we're gonna say, let's get the moving average of 12 months. And we've smoothed it out a little bit. Our spike clearly influences our time series, but you can kind of see with a smoother moving average, we have what looks like sort of a declining trend here. And it's at least kind of stabilized and then drops in terms of nighttime lights for this particular area. Not sure why that is. It might be something to investigate. And then obviously you can imagine going from here. I mean, you can do ARIMA models if you want. You can do Fourier transforms to try to get more precise analysis of the cycles that are involved. You can look at trends. You can cluster on these time series. If you've done time series analysis, obviously you know that there's a whole world of things you can do with these data. But this sort of shows how you can extract data for a particular region and convert it like that. And again, for me, the advantage of this, as opposed to doing this in Google Earth Engine, is that now I have this data in the data frame and I can do anything with it. If I wanted to, I could actually integrate these nighttime light means with data I have on, I don't know, maybe I have mobile data for Olympic Stadium, and I want to see what the sum of mobile devices is on average for particular months, and I want to do some kind of analysis or modeling. Sky's the limit. Actually, space is the limit. Okay, let's do the same thing, but now we're looking at South Korea in general. And this time, instead of just a localized region, we're going to get radiance for the entire area. So we're pulling a geometry. That's the Republic of Korea, South Korea. It's just one geometry. It's for the whole country. This function is almost identical to what we did before. The difference is subtle, and that is, instead of getting the mean, we're actually getting the sum, because we're looking at a sum of lights calculation here. And then we called this variable Seoul, and then we're just naming it SOL, just so we know when we print our data frame later that it's SOL. Otherwise, it's the same thing. We're doing the same process. And from this point on, every step is exactly the same. So we get this, this collection of numbers that are represented by date and sum of lights. It's going to create this sort of nested list structure that's kind of cumbersome for us to work with. So we're going to convert it to a data frame, and then we're going to convert the dates to legible, sort of human readable dates, and then we're going to set the index to the date. And so now that we've done that, we have our variable sol_df. And so now, just as before, we're going to make a map, but instead of, oh, well, this is just actually, we're going to just make a map first of the nighttime lights layer over over South Korea. Interesting. That has happened before. There might be some coordinate reference system thing going on that it didn't center my plot directly on South Korea, which is perhaps something that happened with you guys with Timor-Leste. I've been lazy here. If you guys are geospatial analysts, you know that you never really ignore coordinate reference systems. You can never ignore them. You have to pay attention to them. I didn't really pay attention to what the geometry of these shape files are, and they might be in different projections, and there might be some different weird things going on there. So that's something you want to pay attention to. That's another workshop. But for now, just know that you can navigate to South Korea. And here we're looking at the nighttime lights, which is where we've gotten the median for our entire collection. So this is over the whole time span from 2014 to 2020. I've clipped the image basically, or I'm stretching it between the min and the max of 0 and 10 here, just for visualization's sake. But obviously what we want to do is plot a time series. And so just as before, we have our data frame. In this case, our data frame is called sol_df, but otherwise everything's the same. We're just creating different labels. So now what we have as our y-axis is we have the sum of lights. We have the actual sum of every pixel of light in South Korea within that geometry. Here you also see some cyclical activity. You see what does appear to be a steadily growing trend. So if you just stop right there, maybe that's enough for you to kind of see if there are any trends like this that are associated with economic growth or anything else, or electrification or anything that might be happening. I don't think you should. I think you should continue pre-processing with time series analysis to get this to be a better signal. But you can actually see that this is how you get from the raster file to a time series that you can do further analysis with. And one sort of quick thought here. So we were doing conditioning before on thresholds above and below radiance. We're just looking at the sum of lights for the entire country of South Korea. But let's say you wanted to look at just high intensity areas. You could create separate time series. I'll leave it to you to do this on your own. But given what we learned in the module about conditional operations, see if you could take the VIIRS data and reduce it to different time series for South Korea for different levels below or above certain thresholds of light. Perhaps you can use this to take a look at what low light or perhaps rural areas are doing in time versus highlight or urban areas. It's sort of a way to do that empirically without actually having to define those areas. And obviously, as many of you are involved in, there's a lot of research into actually defining areas of urban versus rural, sometimes based on things like nighttime lights. But that's how you would actually take this time series apart. Here we're smoothing it by 12 months again, as we've done before. And here you see that trend, when we smooth it, is a little bit more prominent. There's actually quite a bit of growth here in 2017. Here's a question for you as an analyst, though, and that is, you want to make sure that you are not calculating what could be some noise that's happening with the sensors, which are, for VIIRS, pretty reliable and pretty constant, but there is some variation. And I'm gonna get to this in the next exercise, but it's one of the reasons why I'm not a huge fan of sum of lights, because when you're looking at an area the size of South Korea, you're aggregating all the data for that whole area. It's a fairly large area. Any small fluctuations are going to be geometrically added here. So there is the potential that fluctuations in the data could make a lot. Now, South Korea is a very obviously high radiance area, so the noise won't matter as much, but it is something that you want to pay attention to. I would rather look at, for time series, things like average radiance or other ways to normalize the data. But that's just an FYI. But my point here is just, this is how you would take the data and create it into a data frame that you can work with, including make a plot. So I'm going to, with that jump, because I do want to get to some of the other stuff we were talking about. Histograms are another thing that you can do. I'm not going to actually work through this notebook, but I'm going to just show you this website, and you can follow along if you want. Again, open this in Colab. Before, as mentioned, I pinned the version before. Another thing you can do is you can just upgrade. So whoever is installing the Seaborn library on Colab, whatever administrator is responsible for that, they just need to make sure they're updating to the most recent library. They apparently haven't done that yet. So I'm manually saying, hey, install and upgrade Seaborn. I know you have Seaborn already, but give me the latest version of it. That's what I'm saying here. And that's what you'll want to run. And the reason you'll want to do that is we're going to make some histograms here. And this method called histplot is not available on the old version. So if you didn't do this and you tried doing this code, it would say histplot is not defined, or Seaborn does not contain histplot, or something like that. So if we're looking at Berlin, here we have VIIRS data for December 2019. And we are looking at the extent that we've defined here as Berlin. And you can see there is obviously some spatial structure here around the city itself. You can even see it followed in the network patterns, or the road network patterns here. You have dark patches where you have river, forest, undeveloped land, probably. And so as we've done before, you want to extract this. And one method you can use to extract the data is something called sample rectangle. The method I used before was EE to NumPy. These are basically equivalent. So if it helps you to know, by the EE to NumPy does the extra step of converting this to an array directly. But this is another way to do it. So I'm taking this image and I'm calling this sample rectangle, and I'm telling it what rectangle, which is the bounding box around Berlin. And I'm saying for the average radiance, get me all of the number, and what this is then is a numerical array. It's a two-dimensional array, and the dimension that it contains is average radiance across the Latin long of this bounding box. Okay, pretty straightforward. Now, when I make a histogram, I'm going to flatten this into a one-dimensional array because that's what I'm going to use to actually pass to my histogram. And there's 100 bins here. You can define that however you want. And when you run that, you get this distribution. Now, like most natural occurring data, you have a skewed distribution, perhaps following a Poisson distribution loosely. We're going to call a log scale here just to help visualize. And NumPy has a native log scale function. So it takes every element in your array and it just applies the base log to it. When you do np.log, it's the base log, the natural log. You could also do a base 10 log or a base 2 log. If you have 0 values, it'll throw an error. As you know, you can't get the logarithm of 0. It's undefined. But if you do log 1p, you're basically, I don't get into it. I got to stop myself. There, basically, you can get the log scale so you can display things. And we see here a fairly distinct bimodal distribution, which is perhaps not surprising. You have high dense areas, and then you high light density, and then you have low light areas in our region. And obviously, as you can imagine, it would be interesting to compare this distribution of lights across time. Does it shift? Does it change across regions? Do you see a distribution like this in other cities in Germany or elsewhere? You can even do statistical analyses with this distribution, non-parametric tests. Are these pulled from the same sample in terms of distribution? There's a lot of good stuff you can do. Here we're comparing December 2019 with December 2018. And this isn't a histogram, it's a kernel density distribution, so it's a little smoother. I like it because it's easier to compare multiple distributions. This is, again, something you can do in Seaborn. You can do it on your own if you want, but all the operations are basically the same. We're getting a sample rectangle and we're displaying them there. We could do the same thing for DMSP. And as Kim mentioned, this is where you really note the difference in these two data sources. So if we're looking at Berlin and we've clipped to Berlin, you can see, first of all, we have, due to saturation, obviously a fairly widespread of what looks like high intensity light here. And that's just because we're maxed out at digital number 63. So we're not going to have nearly as much dynamism here in terms of the radiance. That's very clear visually. And also, if we looked at a distribution, we would see that. So one thing to note here is that obviously higher resolution is helpful for looking. I mean, we understand why spatial resolution is important. The higher resolution, the more precise you can look at it. But when you're doing statistical analysis, including even just distributions like this, it's also important to note that with higher resolution, you have a lot more data. So with vastly more data in the same area, so with VIIRS, if we look at our array that we created that's bound around Berlin, we have 12,400 data points for that single image. For a single image for DMSP in the same area, because the resolution is so much higher spatially, we only have 3,000 data points. So now not only is it harder to look at your spatial resolution, when you zoom in, you can see that you're constrained by spatial resolution. If you're doing analysis statistically, you also have a lot less data to work with. So that's another reason why you can get more robust statistical samples from higher resolution data where it's available. These are all things to consider. And this here is a distribution of the DMSP for Berlin. This is log scale. So these are log scaled units in the x-axis here, but essentially you can see where the saturation happens. Obviously that happens around 63. That's not actually where the values are. It's just where the max of the sensor is. And that's pretty clear when we have our histogram here. Okay, great. We're moving on. I know we talked about doing intercalibration. That's a pretty complicated task to try to do yourself. And I wasn't planning on doing that, and especially with time being limited, I'm not planning to actually work through that, but I do want to show you how you can actually conduct intercalibration. Obviously, it's important. We've mentioned this. If you're looking at DMSP and you're doing time series analysis, because there's no onboard calibration, orbits decay, there's a lot of things happening. You want to calibrate this. And there's been a lot of approaches to this, including stuff that I'm sure that Kim has done, and I know that Dr. Elvidge has done. One of the initial methods that was done by Chris Elvidge produced a set of coefficients, and he did, as Kim mentioned, he looked at an area, I think it was in Sicily, found some stable lights, and was able to calculate coefficients for a reference year for that area. I'll just say you can do that with the things you've learned today, because you know how to find an area and you know how to look at the lights in that area and how you define whether they're stable or not. Well, think about it. You could look at the time series, you could look at the distribution over time, but you could find some area of the planet and select it and find a reference here and determine what's stable. And then you could perform linear regression or some model of your choice on that data in order to get calibrated coefficients. It is a little bit more involved for a workshop, obviously. So I'm not ever going to attempt actually doing that, but you could do that with the tools that we've learned here today. The only thing I would say is that in order to really do the calibration, you're going to want to access all of the files, and it's not really something you're going to be able to do with the API. You're going to be restricted by file size. Now we're getting into an area where if you're actually doing machine learning or modeling on this, you want to go to the source and you're going to set up a data pipeline that actually will train a model on the full image, on the full raster image from the source. So that takes some time. And so one of the reasons this is useful exploration is you might want to find out, well, what source are we actually looking at? Can we determine if there's an area on Earth that we want to choose as our reference point? That's something you could do using what you've learned here today. And then once you've decided to do that, you could say, okay, I'm going to do my calibration model on this area, but now I'm going to have to go and I have to get a data engineer or myself. I'm going to set up a data pipeline to actually pull that from the source and to run my models and do all kinds of fun, crazy stuff. But that's something that's going to be very limiting with the Google Earth Engine. But this at least helps you understand it. And yes, we will have future tutorials that will walk through this. For now, I'm going to say today is that if you reference these calibration coefficients that have already been produced, one thing you can do is just actually use them. And we're going to look at the area over Washington, D.C. And actually, you know what? For this, I am going to download a live notebook. And again, you can do this on Colab with me. All right, intercalibration. Okay, all right. No crazy libraries on this one. We're all just using the basic stuff, GMAP basically. Okay, so here's an area over Washington, D.C. And just for sake of purposes today, we're going to just look at the coefficients for one satellite year pair. So 1996, there's only one satellite, F12. Let's just select that. And by looking at our table above here, we know that for 1996, F12, the calibration coefficients, according to this model, are these three coefficients, okay? And so what we can do is actually say, okay, well, here are our three coefficients. Now, remember we used expressions before, so you can just drop these coefficients directly into your formula. And again, I think I defined that up here. Yeah, exactly. So, and you can look this up in the reference paper, but the formula is a simple quadratic formula. And then you can pass this to your expression and okay, we've just calibrated our image. And what we're going to do essentially is we're going to clip this image because once we calibrate it, some values will go above 63. And we want to make this comparable to other images. So we're going to do, you should recognize this method is greater than. And what we're saying here is, okay, for any pixel that has a value greater than 63, wherever that happens, that's what we're calling here. We are going to set the value to 63. So we're actually changing the values in this matrix or in this image, and we're clipping them at 63. We're going to do the same thing. Anything that's less than or equal to 6, we're going to assign to 0. We're basically going to say that's background noise. We're going to 0 it out so that we're not paying attention to it in our analysis. So that's on our calibrated image. And to make this comparable, let's do this. I don't know if I ran this code or not. Yep, we're going to do this on our original image. So these are both clipped, but only this one is calibrated. Okay, so now we can actually compare what we're doing with these images. And in order to do that, we need to, again, extract the data into a numerical array. And I'm going to just choose this rectangle with these coordinates. The nice thing about interactive maps is you can actually draw squares and all kinds of things here. It's not showing up for me. You can do that. I just for some reason I think the layer is covering it. But you don't have to know what lat long is. You can actually draw geometry and extract it. That's a little bit more involved, but you can read how to do that. But let's say we're taking this rectangle and we're setting that as our geometry. And just like we did before, we're going to convert this to a NumPy array. That sample rectangle and this EE to NumPy are doing essentially the same thing. But with this EE to NumPy function, I don't have to actually convert it to an array type. I know this all sounds like a different language to you guys, but trust me, these are equivalent. And basically what you're doing is you're taking the data in this roster and you're taking the values from the region that we've defined here by this rectangle, and I'm converting this to a numerical array. And just so happens, by the way, this numerical array has 44,000 pixels in it. And I'm doing that so that I can plot a distribution. And this is, I mean, if you're an analyst or a data scientist, I mean, this is your tool, right? Plotting distributions and plotting different things is how you know what's happening with your data. So here you have two versions of the same image. One of them in blue is non-calibrated. This is from the annual composite that we pulled from Google Earth Engine. And then the orange distribution shows the application of our coefficients here. So you can see there is a difference. It has adjusted our image. And so one thing I want to note here is you want to do this thinking programmatically. And so what we've done is, and there are two reasons for this. Obviously, what we did before is I hand looked up whatever the coefficients are, and then I plugged those in manually into my expression here. This is bad for two reasons. First of all, it's time consuming. Who in the world has enough time to go look up individual coefficients and hand plug them into a formula like this? That is incredibly tedious. And if you had to do this every time, you would go insane. Secondly, and more importantly, by far more importantly, as you can imagine, plucking out coefficients like this and editing and hand manually entering them is prone to error. I mean, it might be a small error, like maybe I put in 5.6 instead of 5.9. It might be a big error, like, oh, whoops, this is a different order of magnitude. These are problems, or I guess more probably that would be a different order, whatever. You get the point. You don't want to be doing this manually because you're going to be creating error every time you enter these numbers. So one advice here, and what we've done here in our module is we've created a file where we very carefully enter these coefficients as a CSV file just for this particular model and saved it in the repo. And now we can reference that file. So now what I'm doing is I'm creating a function. And what this function does is it takes an image file, like from Google Earth Engine. And it says, okay, get me the ID of that file, which is the name of the file, which for DMSP we know contains the satellite name as well as the year. Those are both encoded in the name. And then what I'm going to do is I'm going to reference my data table that I created, and I'm going to look up the values for the coefficients. And I'm going to look up each of the coefficients, C1, 0, C1, and C2. So this way, I don't actually have to know personally what the actual coefficients are. I don't even need to know what the year is. I don't even need to know what the satellite is. All I need to do is pass this image, and that metadata is already there. This function will extract it, and it will automatically look up and apply and return the exact coefficients that I need. And so now by defining my next function, I can take the coefficients. So what I'm doing is I'm passing that function that I just created, and I'm saying, okay, give me an image. And now from that image, I want you to return to me the coefficients from our LVIG model here and save those as variables C0, C1, and C2. And then what I'm going to do then is I'm going to create my formula like I did before, but now I'm going to assign these variables dynamically so that I'm going to apply this formula to an image, and I'm going to use the coefficients for that particular image. So now hopefully you can understand the power of functional programming. This is really, really helpful, and I think massively important for scientific research. Why? Because I am documenting how exactly I'm manipulating these images, and I'm doing so in a way that other people can hopefully see and replicate. And this to me is incredibly important. I think to anyone. And so now what I'm doing is I'm also clipping the image. Remember, that's another function that we did. And now I'm combining these, I'm wrapping these in a third function that basically says, okay, do all these things, or a fourth function, do all these things, calibrate the image and clip it, and then return my image. And that's what I'm defining here. Now that I've done that, you will recall that we can actually, if I haven't defined something, let me see what my error is. I don't have saved currently this actual data file. Which is, of course, something you need to have happen. So what I'm going to do then while I'm doing that is open this in Colab where we do have access to it. While that's installing, yeah, so I got to do this. While it's installing, I'll just show you on the website. When you run those functions on a particular image, okay? Yeah. When you run those functions on a particular image, all right, calibrate and clip. That's the image. Those are the functions that we just created, and I'm going to apply that to my 1996 composite. And what I'm going to get is a calibrated image that is clipped and ready to go. And I can also, as I've done before, pass this. So this is the exact same process that we did manually through the expression by hand typing it out like that, right? But this time we're using our functions that we just created. And what I'm doing is a sanity check is I'm plotting the distribution of these two, and they should be exactly the same. And indeed they are, because that is a gut check for me that the functions that I just wrote are performing the same calibration as the manual expression that I entered before. So that's good news. And if I were to subtract one array from the other, the difference is 0, of course, because there is no difference between the two. Okay, so now you can see, all right, if we were to take another image and let's look at two satellites, F-16 and F-15, which we know were observing, they were both observing and collecting stable lights data in 2007. So we can actually compare these two satellites for the exact same year. So we take these images and we convert them again to an array so that we can plot them. And when we look at these two images, we see that they have different distributions. So despite the fact that these annual composites are supposedly for the exact same period of time, because they're from two different instruments, as Kim noted, we have difference here. They are not calibrated. So you can easily see if you were doing time series analysis and you use 2007, first of all, which satellite do you choose? It wouldn't matter which one you're looking at. Second of all, if you're not calibrating across time series, that can be a problem. So here we apply our calibration, and we're doing that to each of our images. And now that we've done that, and again, because we have this function, I don't have to remember anything about the image. I don't have to know what the coefficient is or even what year it is. I'm just passing this variable. I'm just passing this variable for it directly and plotting those. And now you see that the calibrated distributions of these two satellite composites are much more similar. They're not perfectly aligned, of course. Calibration is a model after all. It's an approximation. But you can see that compared to the original sample, these are far closer, especially where it counts when we're looking at the high and the low values that are probably things that are going to matter in our analysis. So there you go. That's how you would, at least according to this one model, create intercalibrated time series. So on your own, could you do this to create a time series? How would you do that? As a hint, well, we have created our calibrate and clip function. So as we've done before, you can map this calibrated clip function to an entire image collection, for example, to the entire DMSP collection. And then what you would get is a calibrated image collection. And then just using what we just learned, you can look at plotting time series or histograms. Obviously, there's a lot more stuff we can wade into. I'm cognizant of time, so we are getting close to the end here. And if you're still with me, we're going to keep going for a few more minutes here because I do want to show some important things. But I hope, again, that you're just getting an idea of how to explore all this stuff. Calculating rate of change is another pretty common operation. Again, I'm not going to actually execute this, but I am going to walk through it. Again, this tutorial is available. One thing, if you're looking at DMSP and we pull the collection for, let's say, 8 years from 2000 to 2007, you'll notice that you get 16 composites. Well, again, that's because we have multiple satellites. So one thing you can do if you want is you can actually apply this metadata filter. So we're taking our DMSP image collection defined here, and we're filtering by date for this period of time from 2000 to 2007, and that's inclusive. But if we do that, we would still get multiple satellites for some years. So let's say, and this is because we've looked this up, so we already know a priori that the satellite F-15 was indeed collecting data from 2000 to 2007. So if we did not want to calculate or do intercalibration, and we just wanted to compare within one satellite, this is what we would do. And so if we're going to calculate the rate of change, that would be advisable. If we weren't using one satellite, and even if we are, we should really calibrate it. But if you're using multiple satellites, you would definitely want to intercalibrate as we did before. Now, the slope is just the rise over run, as we know. So for images, we can just get the first image in our collection, which is the first date, because we've sorted it by time. And then we reverse the sort and get the first image as the last. I'm not going to get into data structures and algorithms, but this sort of sorting is something people have spent their entire lives understanding how to do efficiently. But basically, we're getting the first and the last image. And we're getting the slope by simply saying, okay, subtract our stable lights values for the first image from our most recent image, and then divide by 8, which is our period of time, and you're going to get the rate of change annually. And if we were to do this over Shanghai, for example, we would see our slope of change. This is the annual rate of change. And I'm not a designer, so I picked this sort of puke color of green and yellow, so I apologize. But the orange shows brightness of increasing rate of change, and the green shows a 0 or negative rate of change going into blue. Now, you'll note that we have growth here in the suburbs of Shanghai, but Shanghai itself seems to have had no change or perhaps negative change. Well, we know that this is because of saturation, or we're pretty sure this is because saturation. So this is, again, another example of how you want to be careful doing rate of change or time series with DMSP. If it's maxed out in 2007, the change from 2000 to 2007 is, if it's maxed out in 2000, the change is going to be 0 if it's maxed out in 2007. So that's what we're probably seeing here. And that, as Kim noted, of course, something to note. So if we look at VIIRS and we look at creating the same way we did before, let's extract data for 2000, or this case, from 2014 to 2020. And this is in months, so we're going to have a time series of 73 months. Now we can visualize this and get a much higher resolution for our map. And you can actually see not only is saturation not an issue, And we can see at the neighborhood level. So here we have over Shanghai Airport, over those 7 years, an increase in nighttime lights. Were they doing construction? Did they add a runway? Is there more airport traffic? What's going on there? That might be a question. Whereas in some other pockets nearby, we see that the nighttime lights has actually decreased. So VIIRS is, in this way, a very powerful tool for just visualizing that. And of course, here's a question to you. It's nice to visualize, but can you quantify that? One thing you might do is get cell statistics, like sum of lights, which we did in an earlier module, as you recall. So apply what you've learned and try to get a metric here and see if you can get a time series or quantify some change over time. Okay, let me see. All right, so is my last two pieces here, and I'm going to get through these in the next several minutes, so bear with me, and then we will conclude for the day. But I do think there's some important things to note with this module, which I'm going to actually load really quickly so that I can work through it. Where did I save it? Did I save it in the right spot? Bear with me one moment. Oh, I did, yeah. Oh, yeah, there it is. So here's the notebook. You can open it in Colab, et cetera, et cetera. So we briefly discussed zonal statistics and how you can extract data from a roster file. We're going to do that again here. We're going to do this for the country of Japan. Okay, zonal statistics are pretty important. Some of you had questions about this, but you might want to say, okay, the radiance of pixels is all well and good, but I need to report things at a country or administrative level. I want to get some zonal statistics and do some analysis there. So this is how you would do that conversion. So we're getting VIIRS data. We're going to get it for the month of January 2015, just as an example. So this is one image. And as I mentioned before, we have to make sure that this is an actual image data object. And so we can do that in either of these two ways. This is equivalent. But this variable here is the image composite, monthly composite for January 2015 for the VIIRS stray light corrected data set. And we're going to get the geometry for Japan, as we've done before. So we know what that is. Let me make sure I've executed this code. And then we're going to get the administrative level 1, which for Japan are called prefectural entities. And it turns out there are 47 of them in the country. And so we're going to get zonal statistics for these. So the first thing we're going to do is get zonal statistics for Japan. Now, I showed you reduce region. We've used this before. This should look familiar. There are a lot of other methods you can use other than mean or sum, but those are two popular ones. And again, here's documentation for it. The image that isn't displayed there, but I'm going to remind us that we're looking at the difference between a vector and a raster. And this is going to come into play here because we're taking our vector file, which is our geometry for Japan, and we're saying, okay, take the lights, nighttime lights data from a raster, and for everything that falls within our polygon, calculate either the mean or the sum, whatever we choose here. And so we can apply this reduce region function. So what we're doing is we're taking our image, single image for January 2015, and we're going to get the sum, all right? We want the sum of lights. And we're going to get the sum for that entire geometry. We're passing the Japan national boundary here. And then our scale factor, as we noted before, is in meters. Here we're going to do a scale factor of 500. I just arbitrarily think 500 meters is a fine enough scale. Now recall that the resolution of our underlying data is, for VIIRS, 742 meters per pixel roughly, depending on where you are. That isn't what's happening here is you're actually taking data and you're basically downsampling it so that you can see what fits and what doesn't fit within this boundary. And that's a pretty important step. And you need to set max pixels here because there's a threshold. You can look this up. I want to kind of get through that. But basically what I'm doing is saying, all right, for all the pixels in Japan, get the sum of everything. And I'm going to do that at a scale factor of 500. And when I do that, and this is being calculated on a server, that's why it's fairly quick. Okay, so the sum of lights, that is in the VIIRS unit of watts per squared centimeter per radian, is 3,428,000, et cetera. So that's the sum of lights for January 2015. It's just sort of a raw number. Okay, but let's say 500 meters seems a little bit big. I want to rescale to 100 meters. And it takes a little bit longer perhaps because it's smaller scale, but other than that, everything else is exactly the same. I've not changed my image data. I've not changed my method. I've not changed my geometry. The only thing I've changed is the scale that we're doing this calculation at. And because, as you can tell from this image, pulling data from raster pixels and converting it to some geometric shape means choices are made about whether a pixel is in or not in that. So the punchline here is this: these are not the same at all. These are vastly different numbers. Let me just reiterate, this is an order of magnitude different. I ran the exact same calculation. I only changed the scale factor, and my sum of lights, because of the scale, is 85 million. Okay, why is this? My suspicion, and this is just my theory here, I think there's a lot of other things, is that we're dealing with fractals. You're all familiar with that. A coastline, like the coastline of Japan, is an irregular geometry. And if we have a fairly high resolution vector that's mapping all of these different twists and turns, then when we're trying to apply pixels to it, we have not quite an infinite as in a fractal, but you have a very high number of different convolutions here. And if you know anything about fractals, you know that the area is deceptively complicated when you're looking at these regions. I believe this is part of the reason, and there are others, and maybe others know the reason, but the bottom line is this: when you are aggregating data like this and summing it, your choice of resolution clearly makes a massive difference when the computer is trying to determine which pixels are in or out of your boundary. And if you're thinking about this and you did this exercise and you said, okay, sum of lights is roughly equivalent to economic activity. Here's my regression analysis. Bingo, look at this. Oh, high correlation. And then my colleague does the same exact thing, but they change the scale factor because they don't think it matters, and they get 85 million. How do you explain this? I don't think you can if you don't understand it. So where do you go from here? And this is sort of my soapbox moment. That's why I wanted to note this. First of all, again, I'm not a huge fan of sum of lights because you get into these sort of problems. I would much rather work with data that's been scaled or normalized. The simple way to do that is, instead of taking the sum, just get the mean. What is the average radiance? Now that's a choice that you're making, and you may want sum of lights for other reasons. But if we do that same calculation here, and I've changed nothing, but that I'm changing this to the mean, and I included both the scale factors here, you can see that our average radiance for both scales is fairly similar. This is comparable. This is definitely not off by an order of magnitude. These are averages, so keep in mind that any subtle difference is still a difference. But you can see that this is a little bit, I can wrap my head around this more. So one thing to do is, hey, let's scale data. Another thing is, if you're using time series, then it's probably okay. Because if you're just comparing Japan with itself, then it's not going to matter. If you do the 100-meter scale and you get for 2019 85 million, and you get for 2020 86 million, that's comparable. But if you're comparing different regions, you're going to run into issues. At the very least, be absolutely clear in your documentation with what choices you make. And I make an example of this because if you guys are doing this sort of experimentation, you are the ones making the choice about this data. I wouldn't imagine that the people you're giving this data to necessarily understand intuitively. You need to tell them, hey, this is how I got this value, and make sure that if someone wants to replicate it, they know that. So, just again, doing my sort of public service announcement for data analysis and data science, you have to know that these can really influence results. You can obviously, and I'm mentioning this because I've seen in papers, published papers, where things like this are done, and I don't think it's done manipulatively, of course, but we're familiar with p-hacking and other issues with interpreting big data are out there. It can be easy when you're exploring data like this to sort of play around with things until you get something that looks good. And if you do that and you're making statistical assumptions from it, and you're not documenting those assumptions or choices, you could have a problem, and what you're doing may not be reproduced, and be very careful drawing any inferences from that. I'm going to close this out and just say, hey, we can do the same thing we just did for a particular image, and we can do it for all of the prefectures in Japan. And if we do that, now we can do some fun things, like we can actually create a choropleth, where we're breaking down the images and showing these like that. Okay, that's fun. If we wanted to layer nighttime lights on top of that, here we see, the nighttime light structure is more complex. It is obviously influenced by geopolitical boundaries, of course, but not constrained to them. As you can see, Tokyo is sprawling, but the prefecture that contains Tokyo is going to have a higher ratio of lights than, this is all things you know, but now that we've been able to sort of create these zonal statistics, you can visualize them. You can also do time series analysis. You can do a bunch of things with them. Okay, my last thing, and then we're good for today. And that is, on your own, it might be fun to say, okay, let's take a look at some different cities around the world. And let's choose some geometries. Let's look at Berlin, Seoul, which we've seen before, and let's look at Sao Paulo. So we've seen all these cities before. I'm creating some functions to get the information out of these geometries. This is what's called data wrangling. It is a big part of your time if you're doing data like this. It might not be something you want to spend a ton of time getting in the weeds doing, but if you are working with data, including image files, it is very useful for you to understand how you can convert it from maybe you're getting lists and then you want to convert those to an array. And then I want to do some things with that array. I'm changing the dimensions here by squeezing it. I'm renaming columns to different dates. I'm filtering on things. You can follow this along if you want to figure out what the code is doing. But essentially what I'm getting are time series that are the mean values of, what are we looking at, VIIRs for these cities. And one thing that should jump out at you if you look at these is there's some odd things happening here. If I'm looking at the average radiance for Sao Paulo, it seems far lower than that of Berlin and Seoul. Perhaps that's because it's just a lower light area, but there might be something else going on. I didn't really pay attention to what these geometries are, so I don't really know what these areas are other than their names are Berlin, Seoul, and Sao Paulo. So that might be a hint at what's happening here. But if I were to plot these things, you can see, okay, I have a time series. And again, we have disparities in time, although the time series are fairly stable. I can calculate the rate of change by pixel. I can do it by a region. And when I look at the actual area, here's my first clue. So Berlin seems to be the metro area of Berlin, more or less. Seoul seems to be just the city proper, so we're not actually including the metro area here. And then Sao Paulo, well, obviously we have the state of Sao Paulo. So clearly what's happened is we've pulled the geometry for Sao Paulo, which is an entire state. Now, obviously you don't want to compare a state with two cities just because it happens to be named that. So one first step is to say, well, just know what the geometries are from the data set you're pulling from. But one reason I show this example is that, hey, you can actually look empirically, and in a few moments, less than a couple minutes, just by looking at the data, you should become a good sleuther and say, okay, when I'm looking at the data, my spidey sense says this looks odd to me. And then when I look at the actual data spatially, I can see, oh, okay. So I want to make sure I'm researching this and trying to figure out, okay, how do I get the proper unit of analysis so I can do this? And as I mentioned before, this gets me to my takeaways for today. I'm hoping that this really just gives you tools to help you explore the data, really understand empirically what you're looking at, and understand it enough so that you can spend the more time you might need creating data pipelines, creating models, getting into deep learning, getting into the convolutional neural nets and all the fun stuff. And I love doing that too, but I know it's a pain in the ass to do that unless I understand what my data set is. And one way to do that is these tools of exploration. Think critically about your data and your choices. Okay, that should be obvious, but hopefully this sort of reinforces that. That is something you should be doing while you're exploring. And notebooks are really handy tools for that because you can type the text in. This is kind of a sort of a personal finding, but hey, look, there's some things that you may have learned today that you want to figure out and learn on your own and give you power to address these. Maybe you're someone who has never actually accessed these data and done manipulations with it using Python, and you want to do that, and now you know. But know when you don't want to go down a rabbit hole too. So there's no end to how many ways you can take learning Python or statistical programming or analysis like this. But I would say try to keep to things that you're interested in and be able to understand your level of interest. And I think fourth and perhaps most importantly, hey, let's all support open data and tools. Let's do that by doing conferences like this and workshops. But personally, to be honest with you, I think the most important thing you can do is actually use this data. If it wasn't clear to you before, hearing Chris and hearing Kim speak, there is a tremendous amount of work that goes into open data. Is not free. It is a value that is being provided to society. And if we want to make sure this value is being used and produced and continue, use the data. And if that means learning the tools like this so that you can actually take a look at it and not be intimidated by satellite data and say, I've never been able to get my head around it, that's hopefully that's my bigger takeaway today, is participate and use this data, and it'll be better for all of us. Okay, that was sort of a marathon session, and it is recorded. So I really hope that there were some nuggets that you could pick out of this. And as I hope was shared frequently, and as we will share later, the link to the tutorials themselves. Two things about the tutorials: they are being developed, so there are things I'm going to clean up and change and involve, but feel free to use them and work through them. And secondly, very exciting, we are going to be releasing this archive that Kim mentioned that I touched on, as well as tutorials for accessing these data directly, the daily data at an analysis ready level. So that you can perform analysis, you can do compositing, you can do some different things with the nighttime lights data for both DMSP and the VIIRS day-night band. So we're very excited about that. I'm going to stick around here for a few minutes if you guys have questions or comments. But that closes the session out for today. Sam, I don't know if you want to say anything in terms of closing remarks overall, but I just want to thanks again to Dr. Kim Bao and to my colleagues, Ron and Gabe and Trevor. I know you're on, and your team. Thank you as well for your feedback and work on developing these tutorials. So I'm losing my voice, so I'll stop talking, but go ahead, Sam.
Not much to add, just thank you so much, Dan. And that was really just incredible. I'm so happy that we have this in kind of perpetuity now, and that we can make this session available. And it was a wonderful, wonderful intro to these tools and these data, uses of this kind of data. So I'm just thrilled and can't be more thankful for you doing this marathon session. It was a ton of work, but you really brought it to life. So huge thank you. And yeah, we're going to be continuing to kind of push, like Danon said. One of our biggest goals at the Geo4Dev initiative is to kind of continue to push forward this rallying cry of open data, both generating open data, making it available, teaching people how to use it, and disseminating it, and identifying new uses of it. So keep an eye out for more messages from Geo4Dev, and we're gonna be continuing to provide opportunities like this and other types of opportunities and events. So thanks to everyone. I'll open it up if Ron or anyone else at the Geo4Dev initiative has anything else to add. Please go ahead.
No, just a big thank you to Danon. This was excellent.
Great. Well, not much more to add. It's Friday afternoon for you on the West Coast, and late Friday afternoon for those of us here in the East Coast. So, and if you're in other time zones, then it's whatever time it's at. Great. So thanks again. I'm going to jump off here and sign off, but Sam, I assume you'll follow up with everyone who's attended in terms of all the resources and everything, and we'll go from there.
Yep, absolutely. Thank you again, Danon.